Hi.
All right, so we're recording. Welcome everyone. It's now 1 p.m. Today we're happy to have Dror Bar-Natan from University of Toronto to tell us about his opinions on categorifying the Alexander type invariants. A couple reminders at the beginning. Dror has a preference to see whether we are happy or suffering during his talk, so if possible, please have your video on, but keep your microphone muted unless you have a question. Dror will not be following the group chat on the side, so if you do have a question, just feel free to unmute yourself and ask your question. All right, feel free to take it away, Dror.
So I will be talking about the Alexander polynomial, which is a quantum invariant in a non-standard way. I should say that my talk follows the handout, and it's best if you all have a copy, because then you don't have to be synchronized with me. You can look at it asynchronously. And to find a copy, you go to http://drorbn.net/cat20. Very easy to remember, drorbn.net/cat20. And finally, thank you for inviting me to speak in my basement. It's a joy. And in this seminar, it's an even greater joy. So I actually had sort of a big ideological statement to make, and I wanted to read the whole thing to you. It's also on the handout. So I prepared it in advance, and I hope it will work well. So let me share the screen with you and start. So is it shared? Do you see me? Anyway.
Yes, I see the video now.
Here we go. The Alexander polynomial is a quantum invariant in a different way. On a chat window here, I saw a comment, Alexander is the quantum GL11 invariant. I have an opinion about this, and I'd like to share it. First, some stories. I left the wonderful subject of categorification nearly 15 years ago. It got crowded. Lots of very smart people had things to say, and I feared I will have nothing to add. Also, clearly the next step was to categorify all other quantum invariants, except it was not clear what categorify means. Worse, I felt that perhaps we all didn't understand quantum invariants well enough to try to categorify them, whatever that might mean. I still feel that way. I learned a lot since 2006, yet I'm still not comfortable with quantum algebra, quantum group, and quantum invariants. I still don't feel that I know what God had in mind when she created this topic. Yet I'm not here to rant about my philosophical quandaries, but only about things that I learned about the Alexander polynomial after 2006. Yes, the Alexander polynomial fits within the dogma, one invariant for every Lie algebra and representation. It's GL11, I hear. But it's better to think of it as a quantum invariant arising by other means outside the dogma. Alexander comes from or in practically any non-abelian Lie algebra, foremost from the not even semi-simple 2D AX plus B algebra. You get a polynomially sized extension to tangles using some lovely formulas. Can you categorify them? It generalizes to higher dimensions, and it has an organized family of siblings. There are some questions too, beyond categorifications. I note the spectacular existing categorification of Alexander by Oshvatz and Szabo. The theorems are proven, and a lot they say. The programs run, and fast they run. Yet if that's where the story ends, she has abandoned us, or at least abandoned me. A simpleton will never be able to catch up. If you care only about categorification, the take-home from my talk will be a challenge. categorify what I believe is the best Alexander invariant for tangles.
Let's scroll straight to the end where the Death Star appears. Oops, I lost it. It doesn't matter. We're going to move on with the talk. Okay. So now I'm really starting. So practically all quantum invariants come from the same technique, and let me call it the Young-Baxter technique. And it goes as follows. So given an algebra U, wait, am I still sharing the screen?
Yes, I can see your handout.
Oh, good, that's bad. I don't want to share my screen.
Oh.
Good. I want you to see me pointing. So given an algebra U, and it's typically either the universal enveloping algebra of some Lie algebra or its quantized version, and then given suitable elements R and C, where R is an element of U tensor U, and meaning that I can write it as some AI BI, where AI is in the first U and BI is in the second U. And one of the properties of being suitable is that it should be invertible, and then I can write the inverse as some AI bar, BI bar. And given another element C, which is also invertible in U, I can form an invariant of tangles as follows. So if K is a
Dror, sorry, it's actually hard to see. It's hard to see the formulas this way. You can see, I mean, you can sort of guess, we can have guess what's going on, but we cannot see the indices. And
I see. I'll share again, but then you should try to look at both the shared screen and my image. Okay.
yeah, we'll imagine we'll see you in our minds talking, explaining this.
Actually, view both at the same time.
Also, Dror, could you speak closer to the microphone? I think the sound will be better.
Oh my God, I'm having technical issues. The answer is I can't. Okay, so is the sound reasonable or? Okay, I'll just try to speak louder, but I don't know. Okay, anyway, so given a tangle, K, as shown here on the right, you put a copy of R or R inverse next to each crossing, depending on its sign. So basically, on the first crossing, it's a positive crossing, so I could put a copy of R, meaning I put AI on the upper strand and BI on the lower strand. And then on the second crossing, which is a negative crossing, I put an AJ bar on the upper strand and a BJ bar on the lower strand. Likewise, on the third crossing, I use different indices because I'm going to use them for independent summations. And I put a copy of C on the caps, or maybe C inverse, depending on the orientation. I don't think I should go into it. And then I can read out an invariant. So I go along the first strand, and when I go along the first strand, I see AI, C inverse, BK, AJ, BI. So I write AI, C inverse, BK bar, AJ bar, BJ, BI. And then on the second strand, so I put that on the second tensor copy, I put BJ bar, AK bar, I sum over everything. And if I was lucky and the choice of R was and C was really appropriate, so the most important thing is that R should satisfy the so-called Young-Baxter equation, then ZK is an invariant of tangles. And quantum invariants arise this way. Now, the problem is that typically the algebras we work with are infinite dimensional. So you need to make sense of this sum, or you need to know how to extract information out of this sum without performing infinite summations. And the dogma, the standard way to do it, is to use representation theory. So you pick a representation theory, And instead of putting these elements, you put the matrices corresponding to them. Everything becomes finite and so well-defined. But this is, in principle, it works. In fact, in practice, it works. This is what people always do. But it's very, very slow because you end up needing multiple copies of the representation tensors. And even if the representation is two-dimensional, if you're using multiple copies, you're looking at dimensions like 2 to the n, and that grows really quickly. So it's slow. And also, it actually loses properties. So it's not very well behaved with respect to, for example, cabling a strand. If you cable a strand, you cannot compute the invariant of the cable tangle from the invariant of the tangle before cabling, unless you switch to other representations. Anyway, we plan to do something slightly different. And before that, a Gentles agreement. So by the way, so the Gentles agreement says that everything converges. Please do not ask me about convergence. When I write a series, there is always a reason why it converges. Don't ask me why. I know why, but don't ask. Okay? Now, by the way, the etymology is, so this is used to be gentleman's agreement, but I think this is not right to say. So if chairman became chair, then gentlemen should become gentles. Let's continue. So here is a first example. So let A be the two-dimensional Lie algebra as promised. So it's the Lie algebra generated by two generators, A and X, subject to the condition that A bracket X is equal to X. Let B be a dual with basis B and Y, and it's the dual basis. So B is dual to A, and Y is the dual to X. And I take it as a commutative Lie algebra. The bracket is 0. Let G be the semi-direct product of B and A, where A acts on its dual using the coadjoint representation. So in practice, it means that G is the direct sum of B and A. So it has 4 generators, Y, B, A, and X. And the commutation relations you can figure out are written right here. In particular, B is central, and the bracket of X and Y is equal to B. There is some grading convention, which I should have mentioned because it's only used for convergence and you're not allowed to ask anyway. And let U be the completed universal enveloping algebra of G. And then I claim that the following elements allow you to construct quantum invariants using the procedure of before. So R is the exponential of B tensor A plus Y tensor X, and C is the exponential of negative B over 2. And it's actually slightly better to write it in the following way. So I like to think of my tensor factors as having names. Rather than just having a place, the left factor and the right factors, I want them to have names I and J. So I'll say that Rij is a copy of R put on Ui tensor Uj, so on the tensor factor I times the tensor factor J. And then when I write what R is, I can simply write that R is the exponential of Bi times Aj plus Yi times Xj, where Bi means B placed in tensor factor I, and Xj means X placed in tensor factor J. And here's the theorem. The theorem is that, okay, first of all, the B's are central, so you can pull them out of all expressions. They're like scalars, okay? So let's declare that scalars are power series in the BI's, And in fact, I can restrict my attention to power series, which are rational functions in the BIs and their exponentials, which I will call uppercase BI. And then the claim, and this is joined with Roland van der Veen and actually continues earlier work of Lev Rozansky. And the claim is that if you start with an entangled K that has no closed components, then the invariant Z of K is equal to O, I'll explain what O is in a minute, of omega inverse times the exponential of the sum of two quadratics, so really it's just one quadratic, times, I'll talk about it later. So now let's go back. So O is the normal ordering operator. It means the following. The thing written inside the parenthesis following the O, so the thing written here, is a commutative expression. It's just a power series in the variables AI, BI, YI, XI, and that's it, I guess. So it's a commutative power series, but when I write O of YBAX, I mean take the commutative power series and turn it into an element in the algebra, the non-commutative algebra generated by Y, B, A, and X by putting all the Y first, then all the B's, then all the A's, then all the X's. Okay, so physicists know it as normal ordering. It's slightly more general here. So now I can explain the non-commutative, the commutative power series that appears here. Well, it is omega inverse, where omega is a scalar. I've just defined what scalars were a minute before. And in fact, I should say that if K is a long knot, this scalar turns out to be the Alexander polynomial of that knot in the variable B. Sorry, in the variable B, not T. That's a typo here. And as I will argue, this screams categorify me, but I'll argue this in a minute. I'll argue this later. Then I have the exponential of a quadratic, and the quadratic has two parts. The first part, called L, is a quadratic in the variables Bi and Aj with coefficients Lij, and it's boring. Lij are simply the linking numbers of the tangle. I will not say anything about them any further. Q is more interesting. So Q is a quadratic with coefficients Qij, and in the variables, it's a quadratic in the variables Yi and Yj. And the Qij are scalars, so in themselves, they are rational functions, mostly in uppercase Bi. And again, I will argue that they scream categorify us. I don't know how to do it. That's the problem I'm posing. Anyway, in the case of the algebra we are talking about, the story ends here. So this part disappears. But it turns out that all other semi-simple algebras, so all semi-simple algebras have a hidden parameter, and I will not say what it is, but there is some hidden parameter in semi-simple algebras. Let's call it epsilon. And if you compute the invariant coming from the Young-Baxter technique for semi-simple algebras, taking account of this parameter epsilon, expanding everything as a power series in epsilon, you get here a perturbation series, which can also be computed, and I will not say anything about it any further. That's not the topic of my talk. Are you with me still? Melissa, Lev, can you actually see what I...
Yes, I can see the shared screen.
Okay.
And I can hear you.
Good. Okay, this is what I really want. This is the theorem I really care about. But if all I want is the Alexander polynomial, and today all I want is the Alexander polynomial, Then there is a slightly simpler version, which gives slightly more convenient formulas, and I want to switch to it now. So this is example 2. So let H be the associative algebra with two generator P and X, think momentum and position. And it's in fact the Heisenberg algebra, so the commutator of P and X is 1. Let Ci be e to the ti over 2, sorry, e to the t over 2, where t is a parameter, and let Rij be e to the t over 2 times the exponential of t times pi minus pj over xj, times xj. In principle, I already told you everything you need to know about the Alexander polynomial, because I told you what is the algebra, I told you what are the special elements, and before I told you about the Young-Baxter technique. Compute, and I claim that you'll get an invariant of knots, which in fact extends to tangles because the technique was working for tangles. So basically everything that follows is details. And let me show you the first detail. So the first detail is that Rij, when written in normal ordering, where P comes before X, is written this way. It's e to the t minus 1 times pi minus pj times xj, meaning this is a commutative power series, and if you turn it into an element of the Heisenberg algebra by putting all the p's before all the x's, what you get is the R element that I wrote before. Proof. So proof, I'm not going to go over it. There are more interesting things to do. It's basically a clever use of the Heisenberg commutation relation. And well, I have nothing to say. It's on your handout. You can read it. And it's not particularly interesting. And let's go on and talk about more interesting things. So theorem 2 says that the invariant of any tangle, if you write it in the P before X ordering, can be written as omega inverse times the exponential of a quadratic in P and X, in the P's and the X's, where omega and the coefficients are rational functions in uppercase t, which is the exponential of the parameter lowercase t, which I've put artificially into the R matrix. And in fact, omega is a Laurent polynomial, and the Qij's are rational functions, but their denominator is always omega. So if you multiply by omega, you get back again Laurent polynomials. And they scream, please, please, please categorify us. Not just the Alexander, but also omega times Qij. And again, when K is a long knot, omega is the Alexander polynomial. And well, I owe you a proof of theorem 2, and let me explain where it's coming from. And also something about why you should categorify this. First of all, a bit of packaging. So I want to write quadratics like, or sorry, Gaussians, like the one that appeared in the invariant. So normal ordering of omega inverse e to the Qij pi xj in either of two alternative ways. So one way is to just call it just a formal name, e with variables p1 up to whatever, and then x1 up to whatever, and then brackets omega and q. It's useful for computer presentation. Alternatively, so you see omega is a scalar, and the Qij make a matrix whose rows are labeled by the p's and whose columns are labeled by the x's. So you can write this thing as, well, just put the matrix at the bottom right, put the p's as an extra column on the left, put the x's as an extra row on the top, and in the corner that remains, put omega. So that's just a different way of presenting the same Gaussian expression. Okay, and example. So if we look at the first tangle, so the tangles that I used in the example on the first slide, so this tangle, it's also the first tangle in tangle theory, right? Because it's the first tangle which is not a knot and not a braid. So it's the first genuine tangle. Anyway, if you look at it, I claim that its invariant is as follows. The omega part is 2t minus 1 over t, a Laurent polynomial, and the quadratic part, so the quadratic that appears in the exponential of the Gaussian, is written right here. And if I wanted to write it as a matrix, it looks a bit more complicated, but in general, the matrices are a bit simpler. So, well, this is omega, and here are the 4 entries of the matrix. Are you still with me, Lev?
Yes. What is
Dror,
capital?
how can you derive this formulas in this case? How do you compute the disadvantages?
We'll get there. Okay, this is an example of what it looks like, but we will evaluate it. Okay?
I'm sure. What is T capital?
Uppercase T is the exponential of lowercase t. So uppercase T is the exponential of lowercase t written here, and lowercase t is this parameter that I inserted into the R matrix. So the R matrix is e to the t over 2 times e to the t times something, and the value of the cap is again some exponential of t. Okay? So where were we? Okay, so a little bit of an aside on tangles. So
Dror, maybe can I briefly ask you, so you have a matrix with p's and x's, right? But potentially you have power series with in p's and x's. So here you have a matrix, rows are p's, columns are x's. Yeah. But theoretically,
no.
Or you're saying that your exponential function is just this rational function in p's and x's that you wrote down.
The invariant is a power series, but I claim that the power series is always of this very restricted form. It's a Gaussian. It's the exponential of a thing like this, qij times pixj. And then if I want to know the invariant, it's enough to know what are the qij's. And then the qij's are given by this matrix, and this matrix, I mean, the rows and the columns are labeled by the pi and the xj. It's a matrix that represents a quadratic form.
So in the diagram below, in the 2x2 matrix below,
yeah,
this is what you assign to a single crossing. This 2x2 matrix tells us what you assign to a single crossing. What is the meaning of this matrix?
The slide right now is showing the invariant of the first tangle. So the tangle written here, the 3-crossing tangle written here.
But I thought you said you have some polynomial function in p's and x's, and here you just have a matrix.
Well, this matrix represents a quadratic form. So this matrix, so like t times t inverse minus 1 over t times minus 1 multiplied by p1 and by x1, and then do the same for all other entries. So this becomes a quadratic form. This becomes the quadratic form written here.
And the invariant is always, the invariant of a tangle is always a quadratic form?
And the invariant of this particular tangle is, well, if this is omega and this is q, the invariant of this particular tangle is omega inverse times e to the q, but ordered in the pq or, sorry, in the px order.
And in general, you have more complicated polynomials in p and x.
In general, I mean, this is complicated enough, but right, if you have a very large tangle, you'll get a matrix whose size is the number of components and whose entries could be complicated.
But you always just have a quadratic form in p's and x's. You never have anything more complicated.
Indeed.
You always have just a quadratic form.
Right. For this particular algebra, I mean, as I mentioned in theorem 1, for other algebras, you'll have to add a perturbation series to it.
Thank
But
you.
for this algebra, it's just the Gaussian. Okay. So I want to say a bit more about tangles. So tangles are, oh, sorry, I forgot to erase this. So tangles are an algebraic structure with two operations and two generators. So the two generators are the overcrossing and the undercrossing, and the two operations are as follows. So if you have two tangles, K1 and K2, you can simply put them side by side and call it a single tangle. And if you have one tangle with two components, one labeled I and the other labeled J, you can stitch the two together. So you can connect the head of component I to the tail of component J. So you get one long component and call this component K. And clearly, with these two operations, the overcrossing and the undercrossing generate. Because if you wanted any other tangle, you simply use the disjoint union operation to put a number of copies of the crossing. Basically, you place a number of crossings, and then you iteratively stitch. Well, you connect this to this, you connect this to this, you connect this to this. You stitch many times, and clearly you can get this way any tangle you want. So I should say that there are other operations like strand doubling and strand reversal, and they make sense in our context just as well, but I will not say anything about them. But the point is that if you want to compute an invariant of tangles or define an invariant of tangle, it's enough to compute it on the overcrossing and the undercrossing and to say how it behaves under disjoint union and under stitching. And that's what the next theorem does. So you can, the theorem number 3 says that you can fully evaluate the Heisenberg TQFT invariant of a tangle using 3 rules. The first rule is that the invariant of the overcrossing, where the overstrand labeled I and the understrand is labeled J, and the undercrossing with similar labeling, is given by the following matrix, meaning the omega part is 1, and then the matrix has 2 zeros and 2 non-zero entries, well, where the plus and minus depend on whether you are at the overcrossing or at the undercrossing. And this has a Halmos on it because we've actually already proven it. This is simply the statement, well, the value of the R matrix. So we have already evaluated the R matrix in a previous slide, right, over here. And if you write the value of the R matrix as a matrix, it comes out this, and that's all I need to say. The second statement is also very easy. So if you have the disjoint union of 2 knots, the invariant, so you multiply the omega parts and you add the quadratics, and that's completely trivial if you think about it. And adding the quadratics corresponds to taking the block diagonal sum of the corresponding matrices. So that's the second behavior. And then the last one is the interesting one. So if you have a tangle with 2 components, I and J, and maybe more components elsewhere, and you connect the head of I to the tail of J, I will tell you how to compute the invariant of the result. So first of all, the original tangle, before you connected the head of I to the tail of J, had the matrix. had an omega and a matrix, and the matrix had two special rows and two special columns, namely a row for the pi, a row for pj, a column for xi, a column for xj, and then further rows and columns. And let me just give names to everything. So alpha, beta, theta. Theta is sort of the row vector with n minus 2 things, where which comes to the right of pi and below all the other components. Similarly, epsilon, phi, psi, and chi. And then I claim that the invariant that you get after you stitch, so after you connect the head of I to the tail of j, well, that invariant, in that invariant, the rows pi and pj and the columns xi and xj will disappear and get replaced by a single row pk and a single column xk. And I claim that the new matrix is given in terms of the old one as follows. Well, it's written here, no reason for me to read it, it's just here. I'll explain where it's coming from later, okay? And the scalar part actually also get modified. So instead of omega, we have 1 plus gamma times omega, okay? I should say that there is...
I have a couple of questions. So
yeah.
the entries of the matrix are always rational functions in T, in a single variable T.
Yes.
And if you go up to the picture of two crossings, two I and j crossings, when you say that to a pair of ij crossings, you assign that 2 by 2 matrix, I don't fully understand what you mean. You had the diagram of two, yeah, right. Yeah, you have two crossings on the left, and to a pair of crossings, you assign this matrix, not to a single crossing.
No. For a single crossing, forget this one. For a single crossing, I over j, you assign this matrix with the sign plus. For a single negative crossing, you assign this matrix with the sign minus.
Okay. Yes.
So really, these are two formulas here.
Yes.
One formula for the overcrossing and one for the undercrossing.
And what's the first time when you get non-trivial omega? Because for a single crossing, your omega is 1. So what's the first time you get non-trivial omega?
When you stitch two crossings, so right, if you have one crossing and another crossing, the omega part will be trivial. But if you stitch one to the next, omega gets changed. And it will become non-trivial.
And this looks like some kind of continued fraction because you had gamma and then suddenly it's in the denominator if 1 plus it.
No, I don't think it's that. If you want to compare it with anything, you should compare it with Gaussian elimination. So when you do Gaussian elimination and compute the determinant, you do row and column operations, and along the way, you keep track of the scalars, the constant factors that you've used, and you always kind of multiply them into an accumulator in the side, and this accumulator on the side is omega here.
But it does look like it does seem like some kind of continued fraction because you keep dividing. You had gamma, and now it's 1 plus gamma in the denominator. So if you keep iterating, you get a thing that does look like a continued fraction, but with more stuff. Okay. But I mean, thank you.
So I mean, I can see how you can see this analogy, but when you look at it more closely, it doesn't. The things you get don't look like continued fractions. Anyway, so a minor simplification. So basically, if instead of the matrix A that I've used here, you always switch to the identity minus A transpose, you get slightly simpler formulas. So the stitching formula becomes, well, omega goes to 1 minus beta times omega, and a matrix goes to this formula, which again is a slightly simpler formula. And in fact, if you look at it more closely, you see the row and columns operations. but I don't want to do it right now. But this is what I want you to categorify, okay? So why? So it's the simplest and fastest Alexander for tangles. So maybe it took a little bit to digest, but in fact, if you have an n component tangle, the invariant is only an n by n matrix of rational functions. And that's much simpler than what you typically get in, like, if you look at tensor powers of GL11 representations, you'll be looking at things of exponential size. So this is much simpler, and it's also faster because, well, you know from the experience in other places that once you know how to compute invariants of tangles, you can divide and conquer and get simpler, faster algorithms. So the formulas here might look complicated, but in fact, they are faster. They lead to faster computations of the Alexander polynomial. It easily generalizes to the multivariable case. I made life simple by choosing a single t, but I could have used several t variables, one for each component, and then you'd get the multivariable Alexander polynomial. Well, you'll get a cousin of the multivariable Alexander polynomial. It generalizes to so-called V tangles and W tangles, and if you don't know what they are, ignore. And finally, it generalizes to other Lie algebras. That was the content of theorem number 1. And you can find it, so this bit of algebra is hidden in fact almost any Lie algebra. Basically any non-commutative Lie algebra has this bit of algebra inside it somewhere. So you don't even need to know what is GL11, and I think that's a great advantage. Well, the bad news is that you'll have to deal with denominators and divisions, and so the results are Laurent polynomials, but you still need to know how to divide Laurent polynomials, and I don't know how to do it in a categorified world. Are you still with me? Okay, that's the end of my talk in a sense. I mean, I just told you, if you think about it, I gave you complete information. There is an invariant of tangles whose values on the overcrossing and the undercrossing is given this way, whose behavior under disjoint union is given here, whose behavior under stitching is given here, or in a slightly simpler form here. So you can compute it for any tangle whatsoever, and the result is the Alexander polynomial if you restrict your attention to knots. I'm done giving you the challenge, okay? What remains is to explain where these formulas came from my perspective. So let's do that. So again, where do these formulas come from? So I have about 15 minutes to do it, so I'll do it really quickly, okay? Sorry, not 15. I have more like 8 minutes to do it. I'll have to do it even quicker. The point is, well, there is something that I like to call the Pwt principle, which is that lots of algebras, and in particular the Heisenberg algebra, are isomorphic as vector spaces to polynomial algebras. In fact, the isomorphism is the ordering map which we used before. It's the vector space isomorphism. So if you want to understand, say, the multiplication of the Heisenberg algebra, well, the multiplication of the Heisenberg algebra is a map from H tensor H into H. This is a polynomial algebra. This is a polynomial algebra. Their tensor product is again polynomials. And you get a map into polynomials. So you need to understand maps from polynomials into polynomials. That's all. Okay, and or at least a special kind of such maps. So that's what I want to do next. So first, the convention. If you give me a finite set A, I will let Z sub A be a collection of variables Z sub I as I belongs to A. So these will be the variables for my polynomials. And let's agree that every variable in the world is a Latin letter, and it has a dual, which is the corresponding Greek letter. So the duals of the zi's are the zeta i's, and so the dual of the whole set ZA is zeta sub A. And for the variables we care about, which are P and X, the duals will be called pi and xi. Okay? And now I claim that if you have a linear homomorphisms from polynomials in ZA into polynomials in ZB, so between two polynomial rings, you can associate with it a power series. So a power series in the Greek letters corresponding to the domain, and in the Latin letters corresponding to the range. And the way this works is, well, it's simply called the generating function or the generating series. Namely, well, you pack together all the values of a map L. So if you have a homomorphism L, you pack together all the values of L by computing L of Z to the N here as a multi-index, and taking it like make it a generating function in the dual variable. So you multiply it by zeta A to the N and divide by N factorial. And if you think about it, this is the same as saying apply L to the formal exponential written here. And that's a single power series that codes in it all the values of L. Now, if you want to recover L, well, this is roughly the way you recover the coefficients of a Taylor function, of a Taylor expansion from the Taylor expansion. Namely, you just have to differentiate. If you want to find L of Z to the N, you differentiate N times with respect to zeta and substitute zeta is equal to 0. So, and in general, if you want to compute, so if you have a generating series, you want to find the corresponding homomorphism and evaluate it on a polynomial P, you take this polynomial P, you replace the variables by differentiations, differentiate L, and set the zetas to 0. And then there is also a composition law. So if you have two homomorphisms and you want to compose them, I can tell you how to compose the corresponding generating series. So the composition is essentially by, well, you take the the generating series corresponding to L composed with M is you take the generating series of L, replace its Latin letters by differentiation with respect to the Greek letters of M, differentiate and substitute those Greek letters to 0. And then two examples. So the first example is that the generating function of the identity map, I mean, I'm only showing it because, well, one has to start with something, is, well, if it's the identity map between the polynomials in P and X into the polynomials in P and X, well, it says e to the pi P plus psi X to simply follow this formula, and that's what you get. If you replace L by the identity, you just get the exponential of the pairing. And more interesting, if you start from the R matrix, which we considered before, so it's an element of Hi tensor Hj with T adjoined, and you think of it as, well, you think of Hi tensor Hj as you turn it into polynomials in commuting variables Pi xi, Pj xj, and then you think of it as a morphism from the empty polynomial ring to our polynomials, and then you turn it into a generating function. So the generating function is going to have variables Pi xi, Pj xj, and Greek variables corresponding to the empty set, namely none. So the claim is that this generating function is written right here. It's e to the t minus 1 times Pi minus Pj times xj, but that's exactly the theorem I've asserted before. I've just converted it into a slightly different language. You told me it's 50 minutes. Am I supposed to stop? Can I go another 5 minutes?
Yeah, of course, keep going.
Okay. So the next thing to understand is multiplication. So there is a multiplication map from Heisenberg tensor Heisenberg into Heisenberg, and I can convert it into a map from polynomials in 4 variables into polynomials in 2 variables. So the generating function should be a power series in 6 variables, Greek letters corresponding to those and Latin letters corresponding to those. And I claim that it's this exponential. So the generating function of multiplication in the Heisenberg algebra is e to the minus psi I pi j plus pi I plus pi j times pk plus the last term. Well, the proof is basically the difficulty is in, so I'm not going to show you in detail. I'm just going to say that over here, when you a normal order, you get things like p times x, and then in hj, you get again things like p times x, and you need to know how to swap p's and x's, and you need to know how to do it in bulk, because you might have many x's and many p's. And that's exactly what the Weil form of the canonical commutation relations tells you. It tells you how to swap an exponential of x's against an exponential of p's. And the answer is you get e to the minus psi pi times e to the pi p times the swap thing. And if you trace the definitions and use this Weil canonical commutation relations in the right place, you get the formula that I've advertised. Now, if you look at the formulas I have so far, you see the following. All of them are Gaussians. So the identity is a Gaussian which mixes Greek and Latin letters. The value of the R matrix is a Gaussian that has only Latin letters, and the multiplication map is again a Gaussian, as written here, and it has a part that has Greek letters. So I need to know how to compose generating functions which are Gaussians. Okay, and the Gaussians are unrestricted. They can have Greek terms, Latin Greek terms, and Latin terms. So I don't think I have the time to do it, but I can make a category whose objects are finite sets and whose morphisms are generating functions of morphisms. So whose morphisms are Gaussians. And then I need to tell you how to compose in this category. Well, in this category, you can always take the quadratic part and decompose it into an E part, an F part, and a G part, where the E part is the coupling of the Greek letters and the Latin letters, the F is the Greek coupling, and the G part is the Latin coupling. And now, suppose I want to compose one such morphism with another one. So here, I've kind of written schematically how the E's go from the Greek side to the Latin side, the G's are on the Latin side, the F's are on the Greek side. So if I want to compose one such thing with another, well, composition works by, well, differentiating these using these as differential operators. And if you think about it, it just means you pair the ends here with the ends here. And then you want to know what are all the ways of, say, going from the left to the right after composition. So one way is to go straight, and that's the term E1 times E2. Then you have terms where you go along E from the left to the right, you connect to an F, come back here, connect to a G, come back here, and then exit with an E. So you get terms like E1 times F2G1 times E2. But then you can iterate it a number of times. So overall, you'll get a geometric series here, and you can rewrite the geometric series as 1 minus F2 times G1 inverse. And so the composition law is that the E, F, and G of the output are given by the E's, F, and G's of the input by the formulas written at the bottom of the slide. And if you think a little bit more, you can also figure out what the omega of the output is, and it has a determinant in it. I'm out of time. I'll just tell you, everything is implemented. The implementation is on your handout. If you look at the implementations, it completely imitates the formulas that I have derived before. And using this implementation, I'm not going to go through it. Well, you can prove Reidemeister 3 because that's an identity of tangles. So once everything is implemented, you just type it in and the computer tells you that it works. You can compute the invariant of the first tangle and it comes out what I've promised. You can compute the invariant of 817 and the result is the Alexander polynomial of 817. And finally, you can prove theorem 3, namely you feed an arbitrary matrix into the program, you apply multiplication, and you get the output. That's it. Sorry, I know it was a bit rushed. I'm out of time. Maybe I'll go back to the take home. What was the take home? Categorify what I believe is the best Alexander invariant, and the best Alexander invariant is coming from the Heisenberg algebra in a non-standard way, and all the formulas are on the on the board now. I'm done.
Thank you, Dror. All right, are there any questions?
I would have a question. What happens when you restrict yourself to, say, alternating tangles? Do you see a particular form for the elements in this matrix?
No. Not that I know. I mean, I don't know anything, but maybe somebody else does.
Is there any sort of interpretation of how one should think about those entries in this matrix?
So they are closely related to things that appear in work of Kirk, Livingston, and Wang. So if you search for their papers, you'll find it there. It's basically, well, it's basically the Dror representation generalized to tangles. So if you switch to the variables here, then it's the Dror representation generalized to tangles. And in the multivariable case is the so-called Gassner representation generalized to tangles.
And so in the intermediate entries, so at the end you get the Alexander polynomial, which is a polynomial, not a rational function. But intermediate entries are rational functions.
So, there is always this rule that at all stages, the denominators are always omega. So if you multiply by omega, you get always Laurent polynomials. Now, you can ask, but the formulas have various divisions in them. So basically, the statement written here is that some divisibilities are guaranteed. Okay, it's certain times you know that things are going to divide. I don't have a good explanation for this. I have well, I can prove it but not in a way that's very susceptible to categorification. So I cannot it's a bit hard to say what is the precise condition on Qij, which implies that all the divisibilities that you want will occur, and such that this condition will be inherited to the next stage.
But you haven't tried to compare it to Laurent phenomenon in cluster algebras?
It was always on my mind, but nothing came out of it. I mean, I don't know how it compares.
And maybe one more question. Have you looked into extending this structure to trivalent graphs that describe intertwiners between networks of, planar trivalent graph? I described intertwiners between tensor products of representations of quantum GL11. Can you extend this kind of inductive computation to planar trivalent graphs of that form?
GL11 is not my friend. This does generalize to, again, I mean, because I'm a simpleton, right? I mean, I stay with the Heisenberg algebra, or at most the AX plus B algebra. But anyway, this does have a generalization to trivalent graphs in a way similar to how, if you know how associators correspond to trivalent graphs, it's the same correspondence. The formulas become hairy, which is to say, I don't understand them. I don't understand them yet.
Thank you.
So
I have a history question.
yes, please.
Yeah.
What's the explanation for the relationship between Alexander and the Heisenberg algebra? I mean, is there something deep going on? Was it known? I mean, because I know the GL11 story, the Bureau story, all the other story where I say about the Alexander, but I heard about the Heisenberg for the first time in your talk. So I was wondering whether it was known before, or is that something that you cook up and or we was aware? I don't know.
I think, well, okay, it's a variant of this is in a paper by myself and Roland van der Veen, which is in the references, and the references are on my webpage, so you can just go there and see. There might be earlier thing, maybe probably Lev can say something about it, but I want to say that I slightly cheated. It's not really that I've cheated. So, okay. Example 1, the AX plus B algebra is more quantum than example 2 in the following sense. So here the R matrix is, right, the exponential of B tensor A plus Y tensor X. So it's the exponential of something which is in the Lie algebra tensor the Lie algebra. And that's what you get from things like Chern-Simons theory. So in fact, example 1, so in fact, the AX plus B, if you do Chern-Simons theory with the AX plus B Lie algebra, or with this algebra G, if you simply follow it has an invariant metric, and if you follow the recipes of Chern-Simons theory, you get the Alexander polynomial. Okay? But the second example, the R matrix is not of the same form. The R matrix has a Pj times Xj term, and this is a term which is not in the Lie algebra, it's only in the associative algebra. And so this does not come from, so it comes from the same Reshetikhin-Turayev style recipe, but it does not come from Chern-Simons theory.
Merci.
Lev, can you add something?
I am a little bit surprised. I thought that example 2 is a simplification of example 1, where certain things become commutative. I'm a little bit surprised by your statement. Don't you have?
Also not a. It's also well, okay. So basically, I wrote it as a note, which I didn't here. So you can down at the bottom right of the first page. So basically, the algebra G embeds into the universal enveloping algebra of the Heisenberg algebra, or sorry, maps into the universal enveloping algebra of the universal enveloping of the Heisenberg algebra using the map written here. But this map is in itself quadratic, not linear. So that kills Chern-Simons theory.
You send A to Px, that's your nonlinearity, right?
The nonlinearity is A is Px, right?
Yes. I see.
Again, all of this is quantum stuff. You don't need to know it. I gave you all the formulas that should be categorified. I mean, this is the philosophy where it came from.
There is a story of presenting universal enveloping of Lie algebra in terms of differential operators on a flag variety.
Oh, this is precisely it.
And this is what you're doing.
So basically, every Lie algebra embeds into the universal enveloping algebra of a Heisenberg algebra, because you can always think of well, Lie algebra elements act via the adjoint action on functions on the Lie algebra, and this meaning they are differential operators, and differential operators are always described by the Heisenberg algebra. So this is just an example of that.
Mm-hmm.
So the second story is written in terms of, so this is the case of P1. If I understand correctly, you're telling the GL2 story. That's your example 1. So consider P1, consider its north pole. There is coordinate Z, and there is first derivative over Z, which you call P. So you can express generators of GL2 in terms of Z and DDZ. So in particular, the Cartan element will have in it Z times DDZ piece.
Right, this is this PJXJ.
So you passed from generators of Lie algebra to underlying coordinates and vector fields in the vicinity of the north pole of P1. That's what you did.
Yes, well, it's a bit simpler than what it can be said in a simpler language, but yes, I agree with you. But again, the only reason is technical simplification. I mean, the words here are a bit simpler. The theorem is also valid and is much more interesting if you work straight with the original AX plus B algebra.
Mm-hmm.
So the second step you have to do in order to get your example 1, if I understand this correctly, is that, no, I think, sorry, let me take it back. Yeah, sorry. Have to think. So I think if I wanted to categorify it, I would first ask myself how to deal with representations of GL2 of very high dimension, of long, long, long rows. And you can easily land in tails. So it should not be a story about tails of the Jones polynomial, but something else. Yeah. So I don't know, it's an interesting question, but.
I don't think I expected anybody to solve it in real time.
So what are the references for this work? And
So,
thank you for a great talk.
At the very end, where are we? On slide 39, it says that the references are on drobn.net/cat20. But the truth is that most of them are still unwritten.
But are they available?
Some references are written. You can't see this talk in a written form yet. Okay, let me be even more honest. So theorem 1 is like maybe 2 years old. 2, 3, I don't know. I mean, this I understood very well for a few years now with Roland. The more interesting part is, of course, the perturbation. Okay, but anyway, theorem 2 is about 5 days old. So to some extent, I was tempted to talk about it because it's kind of nice and fresh. So it's definitely not written anywhere. However, it is absolutely correct. There is no chance in the world that there is a mistake in it because it's implemented and the programs run. And this is much stronger than having a proof.
All right, I'm going to pause the recording here, but feel free to stay for more questions unless Dror, if you're tired, feel free to let us know. Let's thank Dror again for a great talk.